Hello everyone. In this lecture we will be going over 2002 USAMO problem number 2. Here's a view of this problem. In triangle ABC we are given the following relationship where S and R are the semi-perimeter and the in radius respectively. Then we would like to prove that triangle ABC is in fact similar to another triangle T whose side lengths happen to be positive integers with no common divisors, and we would like to find these integers, these side lengths. Okay, so to begin with, I would like to simplify the notation. Let's assume that cotangent A over 2 be U, cotangent B over 2 be V, and simply cotangent C over 2 be W. And then what I would like to do next is to make two claims and prove these claims actually. So my first claim is that I would like to show that cotangent A over 2, or simply I should probably say U here because that's how I assumed. So that would be equal to S minus A divided by S minus B times S minus C. So I would like to prove this result. The proof will be based on the properties of the incircle, obviously. So what I will do, I will just draw a typical triangle here. Obviously, I can also go ahead and draw some angle bisectors to locate the center of the incircle here. So therefore, this is our incenter here, and I will call this incenter as I. So obviously here I have some angle bisectors. This is an angle bisector and this is also an angle bisector. This is our triangle ABC. Obviously because these are angle bisectors, I know this is A over 2 and this one is also A over 2. So what I would like to do to begin with, we know that I is the incenter, so these would be the touch points, the foot of the projections from I to the sides ABC. So you can now go ahead and draw that circle if you would like to. But what I really want to is to use this small triangle here. Let's call this point D, E, and F. So use that triangle AFI to establish that cotangent A over 2 here. I already know line segment IF is equal to R. It is the in radius, so that's obvious. However, I do not know the line segment EAF. What I do know though is because I have my in circle here, I know that AF is actually equal to AE. In a similar way, FB is equal to BD and DC is equal to EC here. So using some very simple identities, so for instance, let's go ahead and call this distance K here. These would be L and these would be M here. So therefore, line segment A, for instance, would be equal to L plus M. Line segment B would be K plus M. And finally, C would be K plus L. And also remember that the semi-perimeter is simply K plus L plus M. In this case, L plus M was A, so therefore, as a result, we can easily establish that K here is simply S minus A, and that's what I really wanted. So okay, so therefore, cotangent A over 2, or simply U, we can say, is simply equal to K over R, or simply S minus A over R. Now I will be using an alternative definition of area, using the area of triangle ABC is simply equal to the semi-perimeter multiplied by the in radius. So as a result, I can rewrite this expression as S minus A over area of triangle ABC divided by S. So rearranging it would give us, and then, well, yeah, so let's do it in two steps. So what I have here is S times S minus A over area of triangle ABC. And now I would like to employ Heron's formula for the area of triangle ABC, plug it in, and we get the desired result. S times S minus A divided by square root of S times S minus A times S minus B times S minus C here, and they will cancel out, and I would obviously get this the claim 1. So that proves claim 1. Now my second claim, let me open a new page here, claim 2. Obviously here I will start working with this expression. So cotangent A over 2 plus cotangent B over 2 plus cotangent C over 2 is equal to U times V times W, and further that would be also equal to S over R. So let's go ahead and prove this claim as well. So let's just start with U plus V plus W here. We already in the first claim, in the first lemma, we proved that U is just the square root of S times S minus A over S minus B times S minus C, and we can similarly add the others as well. So let me go ahead and write them down. Over S minus B times S minus C plus the square root of S minus B, S minus C times S minus A plus the square root of S minus C, all divided by S minus A times S minus B. So we can actually simplify these expressions. Well, first of all, let's find the common denominator here. So the common denominator here is obviously S minus A times S minus B times S minus C in square root, and the numerator will come out nicely after you factor out the square root. S will come out as S minus A plus S minus B plus S minus C. But now we know that we have 3S here minus A plus B plus C. A plus B plus C is just 2S, so 3S minus 2S will just give us S. So therefore that would be S square root S all over the same denominator here. So what I would next do is I will multiply both the numerator and the denominator by square root of S. So the denominator will become the area of triangle ABC. So I have S squared over the area of triangle ABC. Oh, actually, even before that, let me just make this following observation here. It turns out that this expression here is simply, so using the claim 1, you can, this thing is simply equal to U times V times W. It's simply the product of these three square roots, and because we have square root S, square root S, square root S, that would give us S square root S here, and then the S minus A will cancel out here, the S minus B will cancel out, the S minus C will cancel out. All you will be left is in the denominator these three expressions. So we have the first part of our claim. Now we need to handle this second part here. So let me continue writing the proof here. So at this point, what I would do is I will now rewrite the definition of area of triangle ABC as S times R. The S will cancel out, so we will be remaining with S over R, and that proves the second part as well. So we have proved this important claim, which turns out to be critical for our solution. So now in the final step, let's go ahead and go back to this initial condition and try to see what is its meaning. So this expression, the left hand side is simply U squared, I should say, plus 2V squared plus 3W squared, and obviously that thing is just equal to 6 over 7 S over R squared. Now let's go ahead and use the fact that S over R is simply U plus V plus W from claim 2. So therefore this thing would be simply equal to, and I will also go ahead and factor out the 7 squared here, so 1 over 7 squared. So inside I would have, let's keep the square outside, so let's go ahead. So it will be 6 times U plus V plus W, or simply 6U plus 6V plus 6W. Now what I would like to do now is to do cross multiplication here, and realizing that 7 squared is nothing but 6 squared plus 3 squared plus 2 squared, and we still have this thing here, so u squared plus 2v squared plus 3w squared here, and the right hand side is simply missing square here, so that's our right hand side, so 6u plus 6v plus 6w here squared. Now look at it as an a1, this one is an a2, this one is an a3, this one is a b1, b2, b3 here. So, and obviously here this expression is nothing but a1 times b1, so this one is an a2 times b2, and so finally this one is a3 times b3. So this suggests that this expression here is nothing but the Cauchy-Schwarz inequality in disguise. So do you guys can see that? So because of that, that gets us thinking, because this is supposed to be an inequality here. However, we see that the equality condition is satisfied. So therefore, we know that the, so let's write that down here, Cauchy-Schwarz inequality has equality condition as a1 over b1 is equal to a2 over b2, which is equal to a3 over b3. So applying this condition in our case would suggest that 6 over u, this implies that 6 over u is actually equal to 3 over 2v, which is equal to 2 over 3w. So therefore we can parameterize the u, v, and w in terms of a new variable here. Let's call that variable t. So therefore that would be 36t, v would be 9t, and finally w would be 4t here. So what I will next do is I will plug these values into the expression u plus v plus w is equal to u times v times w. This is what we got from claim 2. So once you plug these in, it is possible to calculate the value of t here. So all we have now is 36t plus 9t plus 4t is equal to 36t, 9t, and 4t, and solving this for t, we get that t is nothing but 7 over 36. Now we can plug this back in to finally realize that u, or cotangent a over 2 I should probably say, is simply equal to 7 over 36 times 36, that would be just 7. V is cotangent b over 2, which turns out to come out as 7 over 4, and omega is equal to cotangent c over 2, which is, once you plug it in, you will get 7 over 9. So using these results, we can now use double angle formulas to find out the values for, say, sine A, sine B, and sine C. Let me open a new page here. Let me just say double angle formulas. So using those formulas, you can easily obtain that sine A is nothing but 7 over 25. Sine B comes out as 36 over 65. And finally, sine C is equal to 63 over 65. So now I would like to make use of the extended law of sines. Most of us would know the formula for law of sines, which is simply A over sine A is equal to B over sine B, which is equal to C over sine C. However, it turns out that this is also equal to 2 times R, where capital R is the circumradius of our triangle. So what I will do here is I will make these expressions look like this expression here. So in this way I should be able to derive this similar triangle that we've been chasing, t with integer side lengths. So what I will do here, it is possible to rewrite sine A simply as, if you will, 13 over 325 over 7. So please check the algebra here. And then this one is nothing but 40 over 325 over 7. And finally, this one here is 45 over 325 over 7. So therefore, what this suggests is that you can think of this common denominator 325 over 7 as 2r as the diameter, of your circle, and as such, this suggests that we can find a similar triangle with side lengths ABC, 13, 40, and 45, which actually does the trick. So therefore, the side lengths of the smallest triangle T are 13, 40, and 45, where these numbers are relatively prime, obviously. And that actually solves the statement of the problem. Hope to see you in our next video.